Good morning, gentlemen. Today we're going to talk about Section 9.2 tangent lines. So if you happen to have printed the notes from Section 9.1 on basic vocabulary and gone over that a little bit, then you would happen to actually recall that a tangent line is, or a line, array, or segment that intersects a circle in exactly one point. And the point of tangency is the intersection of the circle and the tangent line. So when you look at this diagram, you can say that segment ray BA is a tangent ray, line BA is a tangent line, segment BA is a tangent segment, and the point of tangency is point B. Hopefully what you would do is you would print these blank notes from Canvas and then fill them in with me as we go. And then if you want, you can check out the completed notes as well. All right, so there's a theorem about a tangent line. If a line is tangent to a circle, remember that means it touches at one point and only one point, tangent to a circle, then the line is perpendicular to the radius at the point of tangency. So remember that a radius comes from the center and goes to any point on the circle. So there's a radius and there's a tangent line, line BC, okay, or line AB if you prefer. So we can say that line AB is perpendicular to segment OC, or radius OC, if line AB, that's at point C, if line AB is a tangent line and point C is on line AB. Okay, so let's talk about how you're going to use that a little bit. Segment ML and segment MN are tangent to circle O. So we want to find the value of x. If they are tangent to circle O, and if you see a radius OL and a radius ON, and if ML is tangent, remember that it has to be perpendicular to a radius at the point of tangency. So I'm going to put a right angle right here at L and a right angle right here at point N, and then you can use the sum of the measures in a quadrilateral. Recall that in a quadrilateral, the sum of the measures of the angles is equal to, I know that you know this, 360 degrees. So you can say 90 plus x plus 147 is equal to 360. Add everything together. Add the 90 and the 147, or if you prefer, just add 180 plus 147. You get 327 equals 360. X plus 327 equals 360, and subtract 327, and x is equal to 33 degrees. And you're done. That's it on that one. So moving on to the next page. The converse is also true if a line is perpendicular to a radius at its endpoint on a circle. So if we know for a fact that it's perpendicular, then it must be a tangent line. So we'll call this PQ, and I'll call this TR. If TR, if line TR is perpendicular to radius PQ at point Q, then line TR is a tangent line. So you might sometimes have to determine if a line is tangent or not. And to do that, you can use things like what we're going to do in this very next example. We want to find out if segment ML is tangent to circle N at point L. So let's think about, we don't know that we have a right angle, but what else do you see? You see, so a couple things that you see circle N in the diagram, which is in blue. You have a radius, segment ML, NL, excuse me, and you know that that length is 7. You know the length of ML is 24. And then this is 18 right here. I'll try to highlight it instead. This has a length of 18. So we want to think about how we can find out if there's a right angle at point L to say that segment ML is tangent to it, right? If that's the case, then it would have to be perpendicular, which means there should be a right angle, which means what else do you see besides a circle? You also see a triangle, triangle MNL. And if triangle MNL is what type of triangle, then we can say that it's a tangent line. If triangle MNL is a right triangle with a right angle at point L, then we could potentially say that. So let's see if we can figure out how we're going to do that. What do we know about a right triangle, right? Some of the most recent things that you've used, and one of the things that you use over and over and over again is Pythagorean theorem, right? So a squared plus b squared equals c squared. And remember that if this is true, then you have a right triangle. If a squared plus b squared is equal to c squared, then you have a right triangle. So let's see what we can do. We know that if we have a right angle at L, then that would mean that 7 is a leg. And that would mean that 24 is also the length of a leg. And then we would try to compare it to the length of its of the hypotenuse and see if it's actually equal or not. We want to know, is this going to be equal to the length of the hypotenuse? But we don't know the length of the hypotenuse. That would make MN a hypotenuse. So we want to know, is segment MN a hypotenuse? Like, that's what we're going to have to find out. If that's true, then we know we have a right triangle and we can say that we have a tangent line. But we don't know what this piece is right here. So I'm going to highlight it again. I'm going to highlight it in green. We don't know what this length is right here, but you should. You should be able to figure out what it is, and it's something that we forget a lot. If we have a radius, remember that all the radii of a circle are going to be congruent. So it's kind of like the spokes on a bicycle wheel. If you go around and measure each one, they should all have the exact same length. So this length should also be 7, which means that the whole entire length of MN should be 25. So we want to know, does 7 squared plus 24 squared, does that equal 25 squared, right? So 7 squared is 49. 24 squared is 576, and we want to know, does that actually equal 625, which is 25 squared. So 576 plus 449 is in fact actually equal to 625. So it does come out to be a right triangle. Therefore, angle NLM is a right angle, right? Therefore, segment ML is tangent to the circle at L. At point L. And that's it. Moving on. So, let's talk now about how we can continue to use that idea about tangents and what else we know about them. If we have two segments that are tangent to a circle and they come from the same point outside the circle, like point H, it almost looks like an ice cream cone, then those two segments from H to J, which is a point of tangency, and from H to F, which is another point of tangency, must be congruent, okay? So if HJ and HF are tangent to a circle at points J and F respectively. In case you forgot what that means that point J goes with segment HJ and point F goes with segment HF. Then segment HJ must be congruent to segment HF. Okay, and then here's how we're going to use that in an example a little bit. So in this example, this is how you would read it. You would say circle O is inscribed in triangle ABC. What that means is that the sides of the polygon are tangent to the circle. Okay, so really what that means is if we say that the circle is inscribed in a polygon, then that circle touches the the sides of the polygon at specific points, however many sides it has. Obviously, that's going to be how many points it touches in. So here's what we're looking at. We want to find the perimeter of triangle ABC. So use the theorem that's up at the top of the page about the fact that if we have tangents that come from the same point outside the circle, then those tangents are congruent. So I want you to look at point A, segment AD. The length of AD is 10 centimeters, and there's another tangent segment coming from point A, and that would be segment AF. So segment AF should be congruent to segment AD, and we can put a 10 right there. All right. Okay, so let's try the same thing. We have another point outside the circle, point C, and we have a tangent segment here, segment CF, right? And that has a length of 8, but we also have a tangent segment CE, right? So they come from the same point outside the circle. They both touch the circle. So that means that these two pieces must be congruent. So the length of CE is also 8 centimeters. And then finally, we have another point outside the circle, point B, and we have a tangent segment BD touching at point D and a tangent segment BE touching the same circle at point E. So that means that the length of BD has to be equal to the length of BE, or they're congruent. So that's also 15 centimeters. And then recall that perimeter is the sum of all the sides. So AB plus BC plus CA. And the length of AB is going to be 25, and the length of BC is going to be 23, and the length of AC is going to be 18. So I'm going to say 25 plus 23 plus 18 is going to be the total perimeter. So the perimeter that's 48 plus another 18. That's 66 centimeters. You can correct me if I'm wrong, please. Definitely, if you find mistakes in the notes, then you need to check it and make sure that you let me know if there needs to be a correction. But the perimeter should be 66 centimeters. And we're going to move on to the last page. So the last page is a little bit funky. This is a really challenging problem. Let's suppose you have a dirt bike. I don't know how well you can see it, hopefully a little bit better on your computer, but you have a chain for the gears around the dirt bike, and the chain and gears form a figure like so. You have two circles, right? And you have a chain in the picture. In the photograph, obviously, it's a little bit looser. It's shown as taut or very tight. We want to find the distance between the centers. So I'm going to show you what we're looking for, and then we're going to I've redrawn it down here to make it a little bit bigger. Looks to me like 26.5 and 4. So I've redrawn everything. So the question that we're looking at is we want to know what is the distance between these centers. So here's how you're going to have to work this problem. You're going to have to figure out where, so you're going to divide the figure, and I want you to find the figure that's a trapezoid, okay, because that's the one we're going to be talking about a little bit, into a rectangle and a triangle. And here's how you're going to do that. You're going to draw a segment. So I drew the segment connecting the centers, but now what I'm going to have to do is try to draw a rectangle and a triangle. So I'm going to do it like this. I'm going to start at one center, and I'm going to make it parallel to the tangent line. So I need it to be yikes. So let's just undo that a little bit. I need it to be parallel to the tangent line so that it will have so that it'll make a rectangle a little bit, okay? And that's why I need it to be parallel to the tangent line. So I'm going to make it green, and I'm going to start at one center and draw it so that it's parallel to the 26.5 inches that's the tangent line, and make a rectangle like that. Now it's an itty bitty rectangle. I'm going to highlight the rectangle, okay? I'm going to highlight the rectangle in yellow. Here's the rectangle, okay? So there's your rectangle right there, which is great. We got a rectangle, which means we also, don't forget, we know that a rectangle has 4 right angles. So you have right angles. All my highlighting went away. So let's put that back. See if we can put that back in there a little bit. Maybe that helps a little bit better. It still isn't going to do a great job. That's okay. We'll just live with it like that. Okay, so remember that you have a right angle, not just at the tangent, but if you have a rectangle has 4 right angles. So I also have right angles here. And this dashed green segment, what else is true about a rectangle? Opposite sides are congruent. So this would be 26.5 inches right here. Okay, so when we drew in the dashed green segment, that kind of messed up the radius of our big circle over here, this 9.3 inches. So be careful that you recall that 9.3 was this whole entire thing, right? So let's use that property of a rectangle again. If this is 4.5 for this radius, then opposite sides of a rectangle are congruent, so this is also 4.5. Got it? So what we're going to do is we're going to subtract 9.3 minus 4.5 to get 4.8. And 4.8 is going to be the length of what you have left over. This is going to be 4.8 right here. So 9.3 minus 4.5 is going to give you 4.8. That looks pretty sloppy. I'll see if I can clean that up a little bit. This is the piece that I'm talking about that is now 4.8. Okay? And now you can remember that if you had a right angle inside your rectangle here, that you can also put a right angle here inside your right triangle. And then you have a leg at 26.5 and a leg at the 4.8, and you can do the Pythagorean theorem to figure out the distance between the centers. So we're going to do 26.5 squared plus 4.8 squared is equal to distance between centers squared. And probably what I'll do in this very next step is I'll give it a name. So I'll call that A, and I'll call that M, and that'll make it a little bit easier for us to solve. So 26.5 squared gives you 702.25 plus, and 4.8 squared gives you 23.04 equals, and I'll put AM squared. Okay, so we'll add the 23.04 plus the 702.25. When you add that, you're going to get 725.29 equals AM squared. Don't forget that you now need to take the square root of both sides. So you can do second square root, second x squared, and then second answer on your calculator if you wish. And let's check the directions and see if it said to round to anything. Just says find the distance between the centers, find the distance between the centers. So I'm just going to round it to the nearest tenth, and I'm going to say that the distance between centers is approximately 26.9 inches, and we were measuring in inches. And that's the most challenging problem. You may need to check that a couple of times to kind of understand what's going on, but you have to divide the trapezoid into a rectangle and a triangle so that you can figure out the distance between the centers. And that's it. That's the end of section 9.2. Make sure you get your homework done.